All right, we're going to learn how to graph rational functions, and it all starts with finding the 5 features that we've practiced before and then plotting them on a graph. So what we're going to do in our notes here is the same steps, starting with step 0, which leads into identifying your points of discontinuity, but after factoring. And so what we want to do is look for a greatest common factor in the denominator of 2. And what we'll find is that if we divide this by 2, we'll get 2x minus, divide this by 2, 1. So 2 times 2x minus 1, you set that equal to 0 to find your points of discontinuity. The coefficient of 2 doesn't mean anything, so we can divide that out and just look at 2x minus 2 minus 1 equals 0, which gives us x equals 1/2 as our point of discontinuity. So x can't be 1/2. Now we have to decide if that's a vertical asymptote or a hole, so we keep running through our process. The process is that we next look at the numerator and decide if there's any factoring that can be done up there. Because there's a negative a value, I'm going to go ahead and factor out a -3 if possible, or a -1 if possible, if it really mattered. And it doesn't, because even if I factored out that -1, which is kind of pointless, I have 3x plus 14, and it's not going to factor out with the bottom. So I can just leave it all alone up there because it doesn't actually have a common factor. So now we look to reduce, which it won't. So we have -3x plus 14 over 2 times 2x minus 1. So what that means is this factor that remained produced my point of discontinuity. So this x equals -1/2 is defined as a vertical asymptote. We had nothing reduce out, so we have no hole on this function. So over here on my 5 key details, I'm not going to have a hole this time, but I do have a vertical asymptote, and that is when we're at this 1/2. Because x can't be 1/2, that is defined now to be my vertical asymptote. So keeping track of that over on the bottom right-hand corner of the screen. So now we continue through. We're done with steps 1 through 3, and now we're on to step 4, which is to set the numerator equal to 0, and that will allow us to identify the x-intercept. So I'll just write that down here, -3x plus 14. Setting that equal to 0, it's going to yield x equals positive 14 thirds. And how I do that is just subtract 14 from both sides, and that's going to give me -3x equals -14. Divide both sides by -3, and that is giving me the positive 14 thirds. So as a coordinate, you put that right here, 14 thirds, comma 0. Continuing down the list, we evaluate f of 0 to find the y-intercept. So I'm going to do that up here where there's a little more space. But right now, this is my function. The reduced version is what I'm talking about. So f of 0 is going to be -3 times 0 plus 14 over 2 times 0 minus 1. That's going to give me 14 over -2, because this is going to be a 0, and -1 times 2 is -2. Which reduces to be -7. So the y-intercept is 0, -7. So we put that down here with our y-intercept, 0, -7. To keep track of that, all those points are going to be going on the graph soon. So now we check to see if we have a horizontal asymptote, and that's based on our 3 rules down here. This is our last step, horizontal asymptote. Again, there's 3 rules, and in this case, in all cases, we're just looking at the degree, but this particular case, the degree at the top and bottom is the same. They're both 1 linears. So whenever the horizontal asymptote depends on us having equal degree, we divide our a values. So the horizontal asymptote is going to be y equals -3 over 4. Now, it's a little bit tougher to see in that factored form over here. What I would have to do is see that the degree on the top and bottom were both 1, and I'd have to remultiply these 2's to get 4. So it's more convenient to find your horizontal asymptote back in standard form if you were originally given that, to get that -3/4. So now our job is to take these 4 out of 5 key details, because there is no hole, and then plot them on a graph. So first thing you want to graph is your horizontal and vertical asymptotes. So I'm just going to point at both of them because I'm going to do both. It doesn't matter which order, but I guess I'm going to start with the vertical asymptote at 1/2. So at positive 1/2, you would plot a vertical dotted line like this. And then I would get a horizontal dotted line at negative 3/4. And we're just kind of approximating here. And so here is my horizontal asymptote. Now, the deal with the vertical and horizontal asymptotes is you can never cross, and then it's possible to cross the horizontal asymptote, but not every time. It's just talking about the end behavior of the horizontal asymptote. Technically, the vertical asymptote is also talking about end behavior, but you cannot cross. It's a point of discontinuity here, and these ones you can cross in some cases. But continuing down the list, we've got a X-intercept at 14/3, and so we're just approximating. That's almost 5. So we're going to put an X-intercept at almost 5 right there. And then a Y-intercept at 0, -7. So 0, -7. Now here's the deal with these rational functions, is they are supposed to kind of hug the boundary line. So they hug either a top corner or a bottom corner, but not both. But we know which one of these two it's going to go into. So it's either going to go in this top left corner or this bottom left corner, but not both, because you can't have a function be over top of itself. And our key is that we have a coordinate that we know. We know this dot down here, so it can't be up here. It has to be this little curve down here. So it's going to be a function, if we're just kind of rough sketching it, that looks something like this. And then it takes off, and it doesn't touch that vertical asymptote, and it takes off horizontally, and it doesn't ever touch this horizontal line. End behavior goes toward that negative 3/4, and as we get closer to the x value, we take off to negative infinity. And then on the same thought line, in the right-hand side of this vertical line, we're either going to hug the top right-hand corner or the bottom right-hand corner, but not both. And we have to choose the one where we know something. We know we have a coordinate right here, so it cannot be in the bottom right-hand corner. It has to be in the top right-hand corner. So the correct rough sketch of the graph would look something like this. Bottom right-hand corner would not be there. So this would be a rough sketch of the graph. And now what we're going to do is look at how we can play on delta math. So what you do on delta math is you click the thing that you want. I want a vertical asymptote, and then I want that to be at 1/2. So you kind of approximate about right in there. And then we need a horizontal asymptote at negative 3/4, so about right in there. And then we click, I want an X-intercept, and that's supposed to be just shy of 5, so it's at 14/3, so I just go just to the left of 5. And then I need a Y-intercept at -7, so I bring this down and then let it go. I don't have a hole, so I just don't click that. And then it says plot rational functions, so you don't have to do any of the rough sketching part that I did just a moment ago. Delta takes care of that part for you, and it connects the graph with the only logical way that it could go through, just as I discussed a moment ago, and gives you a rough sketch of the function. And then you click submit, and you get a green check mark if it's right. And then it goes through and shows you a beautiful graph of what it was supposed to look like if we had graphed it on a calculator. All right, working through the second example, we're going to keep working our 5 steps with a step 0, of course. Well, now with our step 6, horizontal asymptote. But first step would be factoring the denominator, factor out a -5, and we would see that we have an x plus 1 scenario in the denominator. And our job is to continue to set that equal to 0 and solve. And this -5, of course, would divide out to the other side and disappear, and we get x plus 1 equals 0. And then you subtract 1 from both sides and get x equals -1 as a point of discontinuity. We're supposed to say that x can't be -1. Ultimately, my domain is all real numbers, comma, x can't be -1. And then the next couple steps is just deciding what is that -1. And that happens by factoring the numerator. There is a greatest common factor of x, And so I'm going to divide out an x and make this x times x plus 1. And then I'm going to rewrite my denominator over here, bringing that -5 back. -5 times x plus 1. And what we notice is that we have a common factor, a common binomial factor on the top and bottom of x plus 1. Anything divided by itself, anything over top of itself, just divides out and becomes a very large yellow one here. And we get a reduced version of this fraction to be x over -5. Now, the key here was that the x plus 1 canceled out. It reduced out, which means that produced a whole when x is equal to -1. Now, down here, I need the actual coordinate. So -1 comma what? Well, the what is always f of that value in the reduced version. You can't plug -1 into the original function. That will fail and get an undefined result. So we need to go right here with it and make it -1 over -5, which cleans up to be positive 1/5. So my whole is at -1 comma 1/5, which we'll store right over there in the bottom right-hand corner of the screen. Continuing down the list, we have no vertical asymptote because there was no other undefined point of discontinuity moment. And so we just gonna roll down to step 4. So now we take the numerator, which is just x, and set that equal to 0 and solve. Well, it's already solved. There is a x-intercept at x equals 0, which means that the y-intercept will also be 0. Because if the x-intercept is at 0, the y-intercept, it's the origin. So we don't even have to do any work here for step 5. It's already done for us, because if I plugged in 0, it'd be 0. And finally, we're going to identify the horizontal asymptote. The horizontal asymptote is based on the degree of the top and bottom, and this time the degree of the top is bigger than the bottom. So the numerator has a higher degree than the denominator, and so our job is to say that there is no horizontal asymptote in this scenario. This graph's going to actually look like a line with a negative slope, something like that, and then a hole on the line. So now we're going to take that information and get a rough sketch. So we're just going to, oh, and I didn't cross out vertical asymptote. So we're going to plot these 3 things on a graph. So we take and plot our x-intercept. X-intercept goes right there. And then our y-intercept is the same spot. So of course, 0, 0 is the same spot. And then we're going to have a hole at -1, 1/5. So -1, positive 1/5, which is really small, right here, there's going to be a hole. Now, what that means is there's going to be a graph that actually goes through that hole, comes out the other side looking like this. So ultimately, we could have just used this -1/5 in mx plus b form to have graphed, where we recognize our slope is -1/5 and our y-intercept is 0. So we had 0 and then down 1 over 5, which I definitely missed, but that's okay. It's just a rough sketch. Down 1 over 5 right here, and then connected those dots. But here, we're just getting a rational function rough sketched in there. So our graph would have looked like this to be more accurate. And so the difference between this line and this function, this original rational function, is the fact that there's a hole right here. So it's just a line that we would have graphed in Math 1, Algebra 1, but it has a hole in the graph. So using my tools here in Delta Math, what I'm going to do is plot the x-intercept, and then you drag it over here. And then you have to click, I believe you have to click y-intercept also, and then drag it to the same dot. And then we don't have a vertical or horizontal asymptote, so you got to put the hole in the right spot, which should be at 1/1/5. And we're going to try to be really close to that line right there. We'll call that 1/5-ish, and that should work for us. And then you see my slope's a little bit off, and it might or might not accept it. Let's actually see if it'll accept it. It might say no. Oh, let me have it. So what it lets you, again, it's giving you a rough idea. It's letting you approximate. You see how tight the answer is supposed to be. And it went through that dot that I had plotted when I did it by hand at -5, 1. And using the slope, you go down 1, right 5, and you'd hit that dot. But our job, you see my graph was not exactly the right slope. I missed it. And I saw that before I submitted. I just wanted to see if it would accept it. You just have to be in the right ballpark here. Again, that's the whole idea we're going with rational function, is getting a rough sketch, because we know we could have a perfect graph if we used a graphing calculator like Desmos. Now, the deal with Desmos, if you do that, let's check out Desmos a second. So if I graph this on Desmos, what you're going to see is it really just looks like a line. So if I graphed the function x over -5, you're going to see that it's identically the same. But it's actually not identically the same. And what we're missing here, and what you're not going to see if you just graph it on Desmos and think that you're getting the right answer, you're going to miss that there's a hole right here. See, if you zoom in, like infinitely close, right here, you're supposed to have a hole right there. But you can't see it because it's infinitely tight to the left and to the right of 1. There's infinitely small of a gap there. But if you drag along here, Desmos will tell you it's there. If you hover right, if you click and hover over that spot, all of a sudden you see it go very, very slightly short of that height, and then all of a sudden it'll go undefined, and then it goes right past it to the other side. So you got to be very careful to actually hit the actual dot. So Delta knows it's there. It's just if I'm not clicking on it, you won't ever see it. It's literally as tight together. If you pushed your 2 fingers together on that line, like actually touched your fingers together, that's how tight that gap is. It's so small, it's like the atoms in your fingers pushing away from each other. It's how small that hole is. So if that excites you, cool. If it doesn't excite you, cool. But that's how small it is, that hole that's in there. So we graph it with a rough sketch, and we put this big ominous hole there, and that's kind of how we just get our knowledge to demonstrate itself on the graph. But it's just so tight you wouldn't even see it if a graphing calculator wouldn't demonstrate it for you. All right, on this next one, we're going to roll through our steps, and we've got a little bit more factoring in our future. We got a difference of squares on the bottom. So factoring the denominator to identify our points of discontinuity, we'll have that special difference of squares. So x plus 3, x minus 3. And we set those equal to 0, and we get x equals plus and minus 3. Are the points of discontinuity. But I want to specify which one's which. This one's going to produce x equals -3. This one's going to produce x equals +3 if I set each of those equal to 0. Now, why I care is because one of them is going to reduce out, and I need to know which of these is which as I sort. So it's just saying which ones, just those points of discontinuity is not good enough. I need to specify as I go through. So step 2, factoring the numerator, I have a -4. I'm going to force to factor out and make it in common. So I'm going to say -4 times x plus 3. And when I put that over my factored denominator of x plus 3 times x minus 3, I can reduce out the x plus 3, which means over here, this x plus 3 produced the point of discontinuity of -3, which means that -3 is a hole. And so we're very specific of which x came from which factor so that we know which one produced the hole. And this x minus 3 produced this x equals 3 point of discontinuity. So immediately that one is a vertical asymptote. So sorting through our process here. So vertical asymptote is x equals 3. And the hole, I have to do a little bit more work. I have to find my f of my reduced version, not the original one, the reduced version, which I don't quite have yet because I didn't cross it out, of -3. So now we're going to make this x plus 3 over x plus 3 a big ominous sideways 1. It's a 1. And rewrite the function to be -4 over x minus 3. And then we go ahead and substitute our -3 into this function. That's the reduced version I'm talking about. So we're going to get -4 over -3 minus 3, which is going to produce a -4 over -6, which should reduce to be a positive 2/3. So my hole is at the coordinate -3 2/3. So we're going to store that in the bottom right-hand corner here, which is -3 2/3. And then we continue down our list. We're done with the classifying our points of discontinuity. So we're going to set the numerator equal to 0. Well, that's going to be awkward because we got -4 equal to 0. And that should immediately say in our brain, that's not true, which means you have no x-intercepts. So you just cross that one out. This graph is not going to touch the x-axis. So then we go ahead and do step 5, which is to evaluate the function, the reduced version, at f of 0. So we're going to say f of the reduced version, which is negative 4 over 0 minus 3, and that will produce a positive 4/3, which is basically 1 1/3, but we're going to leave it as 4/3, but just on the graph, it's 1 1/3. So the y-intercept is 0, 4/3. Last thing we have to consider is whether or not we have a horizontal asymptote, and that's all based on degree. So we look at this reduced version or the original version, doesn't matter which one. We'll see that the top degree is 1, the bottom degree is 2. So my horizontal asymptote is going to be y equals 0 anytime the top degree is smaller than the bottom degree. And that's because as we take off to infinity, it causes the bottom to be much, much larger, which squishes the fraction to become essentially 0. So now we're going to plot these on the graph. Vertical and horizontal asymptotes are the easiest place to start. Horizontal asymptote is 0. So pardon my sad dash line sideways, but we'll get the point here. And then at 3, we get a vertical asymptote there. And then we go ahead and plot our y-intercept at 0 and about 1/3. So 0, 4/3 is about right here. And then our hole will be at negative 3 2/3. So negative 3 and then positive 2/3 right in there. There's going to be a hole. Now, the rational process to graph means that the function either has to go up here through those dots that I have, which makes a lot of sense, or down here where I have no dots. Well, that's not possible. So it must be that top left corner. So on the bottom right-hand corner, it could be here, or the top right-hand corner, it could be there, but it can't be in both locations. So the way to actually figure out which side it's on is going to be to plug in a value like 5 or anything right of 3. So if I go back to my reduced version and I plug in a value right here like 5, this will be negative 4 over 5 minus 3. And then we're just seeing if this is positive or negative, and we should get a negative 4 over 2. Now, the point is that it's negative, which means that this graph has to be the right one. This top one is impossible because my result has to be negative. So my graph's going to be this top left-hand corner and this top right-hand corner. So in delta, to get it to work for us, we click vertical asymptote at 3. We get our horizontal asymptote to be the x-axis. And then we have a x-intercept. We don't actually have an x-intercept. A y-intercept at 1 1/3. So we drag that down right there. And then we have a hole at negative 3 2/3. Oops, not grabbing the right dot there. Grab the whole dot at negative 3 2/3. Right in there. And when we click plot, it fills in those 2 dots, and then it auto-generates the right bottom right-hand corner function and doesn't give us anything on the top because it is supposed to be down here, not up there. And if we click submit, we get the green check mark. This will be the right graph for us. All right, we've got factoring on the top and the bottom. We got a nice trinomial working for us in the numerator this time. So running through the process, we'll see how this problem plays, if it's going to play nicely or not. We got to factor the denominator to identify points of discontinuity. We've got a 2 in common, a GCF of 2 in the denominator. We get x squared minus 4. And hopefully we can recognize right there we have the difference of squares to continue our factoring process. So we could solve this by the square root method. It's just not going to help us down below. I need to do this by factoring, solving for my points of discontinuity by factoring. So I got x plus 2 and x minus 2 in the denominator, which is going to give me zeros at 2 and negative 2. And again, please don't fall for the trap that one of the answers came from this coefficient. It didn't do anything. You just divide that 2 out and it disappears because it's just gone. But this gives me an x equals negative 2, and this gives me an x equals positive 2. And that's important to know which one produced which point of discontinuity as we continue down to reduce the function to decipher whether we have a hole or a vertical asymptote at either location. They could both be holes or they could both be vertical asymptotes. Depends on the function. So we got to continue by factoring the numerator. Well, this time the numerator is going to require a GCF of negative 3. So if I pull out the negative 3, all the signs should change. So I got x squared minus 3x and then plus 2. And then if we factor with our magic, the x, I'm going to put the x right here. We put the 2 times this 1 on top to be a 2 and a negative 3 on the bottom. So that my magic numbers are going to be 2 and 1, and both of them have to be negative to get that negative 3 to work and the positive 2. So because the a value is 1, I don't have to do all the grouping work. So I can rewrite this to be negative 3 times x minus 2 times x minus 1. In the denominator, I'm going to bring my factored version that was in green right up over here. Leave that 2 out in front. So 2 times x plus 2 times x minus 2. So now that I factored the numerator, I can do my next step, which is to reduce the function, this x minus 2 binomial and this x minus 2 binomial in the denominator. They reduce vertically. So that's kind of a slanted one. It's a big 1. It's just kind of tilted. And the function reduces to be negative 3 times x minus 1 over 2 times x plus 2. Now, again, the reason why we care about which denominator factor canceled is because that tells us right over here that this positive 2 that came from this x minus 2 is a whole. The other one, the x plus 2 that is remaining, is a vertical asymptote. So this x plus 2 is a vertical asymptote. And so we can bring that right over here. Say vertical asymptote is at the negative 2. And when I said x plus 2, I meant the x plus 2 produced the negative 2. So negative 2 is where my vertical asymptote lies. Now my whole will be at f of positive 2 in the reduced version. So I take my reduced version right over here, and I plug in a 2 to it. Version should be negative 3 times 2 minus 1 over 2 times 2 plus 2. And so that's going to, on the top, work out to be 1 times negative 3, which should be negative 3. The bottom should be 4 times 2, which is 8. So negative 3/8 is the y height of the hole. So the hole should be at the location 2, comma, negative 3/8. Hold that in the bottom right-hand corner and continue down our list. Let's change some colors. So we got a lot of red on the screen. So moving on down, remaining numerator equal to 0. So we've got negative 3 times x minus 1, set that equal to 0. The negative 3 doesn't matter because you divide it to the other side if we're just looking at x minus 1. So x equals 1 will produce the right, to cause the numerator to be 0. So x equals 1 is where my x-intercept is. So 1, comma, 0. If I plugged in 1 in the numerator, I get 0 as a height. Moving down the list, step 5. So evaluate f of 0. So now I plug in 0 to the reduced version, which for space I'll go ahead and do right here. So if I plug 0 in right here and right here, that's going to get negative 3 times negative 1 over 2 times 2. So that's f of 0. And that's going to produce positive 3 over 4. So this is my y-intercept. So bring that right down here, 0, comma, 3/4. Finally, the horizontal asymptote is determined by my highest degrees. Easiest place to look is back in the original standard form. You see my degrees are both 2, so divide my leading coefficients, and I should get negative 3/2 to be my horizontal asymptote. So negative 3/2 is where that horizontal asymptote will go. So now we just need to plot all this information. This is the first time that we have all 5 components in one place. So horizontal vertical asymptote, easiest place to start. So vertical asymptote at negative 2. And then my horizontal asymptote is at negative 3/2. We've got a x-intercept at 1, 0. We've got a y-intercept at 0, 3/4. Right in there. And then we've got a hole at 2, negative 3/8. 2, negative 3/8. right in there, something like that. Now, when I go to get a rough sketch, I know that this right-hand side is pretty well determined. It has to go through those 3 dots. So it's either that corner or it was the bottom corner down here, but I have no more y-intercepts, so I can't have the function down here. That's impossible. So we go ahead and focus on the top. And then we have to determine, is it in the top left-hand corner or the bottom right left-hand corner? And what we know is that we have no more x-intercepts. There's just this one. This is there's only one x-intercept that we found. So that means that this is impossible in the top left-hand corner. It has to be the bottom left-hand corner. So top right-hand corner and bottom left-hand corner is where the function would be. So using our delta tools, click vertical asymptote. And then the horizontal asymptote's at -3/2. Right in there. And then we've got an x-intercept the y-intercept, and then a hole right in there. A little bit tighter. So that should match up with my graph that I've got here.
Go back to the slide
All right, in this final example, we're going to have a denominator that has a -1 GCF. So as we go to factor the denominator to identify our points of discontinuities, we're going to divide out a negative and make this positive x squared positive 3x -4. And then we're going to factor with the magic x on the bottom, which is going to be a -4 on the numerator and a positive 3 on the bottom denominator, or the top of the x, bottom of the x. And we have magic numbers of 4 and -1. 4 times -1 will get me the -4 and add to be the 3, which means that my denominator factors to be negative times x plus 4 times x minus 1. Our points of discontinuity will be x equals -4 and x equals +1. If we set that equal to 0, each sign will change, moving to the other side. Then we can factor the denominator and reduce so we can determine whether these are holes or vertical asymptotes. So the numerator has a 3 in common. So I'm going to write that as a GCF factored out 3 times x plus 4. And the denominator, I'm just going to rewrite back underneath there. Negative times x plus 4 times x minus 1. And then we have our x plus 4 is in common in the numerator and denominator, the binomial. So I'm going to divide that out, reduce it out, so that I can have 3 on top over negative x minus 1 in my denominator. That means that this plus 4 factor right here produced that x equals -4 point of discontinuity. That is a hole. That means the x equals 1 remained, and that is a vertical asymptote here. So we're going to take that over here, put vertical asymptote as x equals 1. And my hole is going to be at -4, comma, something, which we find out by plugging in f of -4 into the reduced version. So we take 3 over negative times -4 minus 1. And that's going to give us 3 over, this will be -5 times negative will be +5. So 3/5. So this hole down here is at -4 3/5. And we continue down our list. So we found the hole in the vertical asymptote. Now we set the remaining numerator equal to 0. And we've got 3 equal to 0, which doesn't make any sense, which means I have no x-intercepts. None. So I take this over here and cross it out. no x-intercept. To find the y-intercept, I plug in 0. I need f of 0, the reduced version, which is going to be up here. Plug in a 0. That's just going to be 3 over negative 0 minus 1, which is 3, because this is negative 1 times, well, 0 minus 1 is negative 1, times negative 1 would be positive 1. So 3 over 1, which is just 3. So the y-intercept is at 0, 3. And to finish my analysis, I just have to figure out where the horizontal asymptote is, and that's determined by the original function's degree, the numerator and denominator. The denominator has larger degree, so that means that this will be a horizontal asymptote of 0, is that rule of my 3 options. So the top degree is smaller than the bottom, which means horizontal asymptote 0. So now we got to plot that information. Horizontal asymptote of 0, start there. It's a nice little blue dashed line. It's kind of rough sketch there. And then a vertical asymptote at x equals 1. And then we don't have an x-intercept because in this one, the horizontal asymptote is the x-axis, and so we're not actually touching it this time. And then the y-intercept is at 0, 3. Not to say you couldn't have touched the x-axis. It could have went through it, but it doesn't. And then on the whole, we're at negative 4, 3/5. So negative 4, 3/5, somewhere right past halfway or something. Now, our options are that the graph on the left-hand side of the vertical asymptote could go through the top left-hand corner, through our dots, which would make sense, or it could go down through the bottom left-hand corner, which is impossible because we would need an extra y-intercept down here, but we have one up above, so it's going to be in the top left-hand corner. Now, on the right-hand side, it's either going to be in the top right-hand corner or the bottom right-hand corner, and I don't know which one to use unless I actually plug in a value that's right of the vertical asymptote, like 2, and see if I get a positive or a negative result. So I just go back to my reduced version, which is this 3 over negative x minus 1, and I'm going to plug in a 2. So 3 over negative 2 minus 1 is going to work out on the bottom to be a positive 1 times negative 1, so it's going to be a 3 over negative 1, a negative result, which means negative wins. So I'm down here with this graph, and I'm not up here, so I erase that part. That was my option, but negative wins, so this is the final graph, bottom right-hand corner, top left-hand corner of the grid. We go ahead and click our vertical asymptote in and drag it over to an x value of 1. Our horizontal asymptote is the x-axis. Plot our y-intercept at 3. And then we need a hole over here at negative 4, 3/5. And we should be able to click plot and get the graph to work for us. And again, the reason why it's in this bottom right-hand corner is because if you plug in a value like 2 into that reduced version, you get a negative output.